Okay, last time we have seen about work and energy. Today we will start from this example. So the example says that a 0.600 kilogram particle has a speed of 2 meters per second at point A and kinetic energy of this one 7.50 joule at point B. So the first question is, what is the kinetic energy at point A? Kinetic energy at point A, and the second question is speed at point B, and the third one is the total work done on the particle as it moves from point A to point B. Now let's start from the first one. It says that find the kinetic energy at point A. We know the mass of the particle and the speed of the particle at point A. So we know that the kinetic energy is equal to half mv square. We have the mass, we have this speed value, so we square it. Becomes 4 multiplied by 6. How much do we get? Divided by 2, 1.2 joule. So here is the formula. Kinetic energy at point A is equal to half mva square. 0.6, 2 square is 4 multiplied, this one is 2.4 divided by 2, 1.2. So the work is 1.2 joule. The kinetic energy is 1.2 joule at point A. So the second question is speed at point B, because the kinetic energy is known. The kinetic energy is known at point B, which is 7.50 joule is the kinetic energy at point B. So when you use the formula where kinetic energy at B is equal to half m times vb square, we know the kinetic energy, which is 7.5. We know the mass, which is 0.6. We don't know only this value. So multiply this one by 2, both sides by 2, then we'll get 2 kV divided by mass. It becomes 2 k sub b divided by mass under square roots. Then we'll get v, the speed at point B. The speed at point B is 2 multiplied by the kinetic energy, which is 7.5 joule, divided by the mass, which is 0.6 kg. And 25 under square root, we'll get 5 meters per second. And the last one is the total work done on the particle as it moves from A to B. As it moves from A to B. So at point A, it has the same amount of kinetic energy. At point B, this amount of kinetic energy. So we need to get the difference between this kinetic energy. First, we need to get the kinetic energy at point A, and then the kinetic energy at point B. So the difference will be the total work done on the particle as it moves from A to B. Therefore, total work done is, we need to find the kinetic energy at point B minus the kinetic energy at point A. So we have to get the difference. We don't need to add them together. Not necessary to add 7.5 plus 1.2. Adding this, we have to know the total kinetic energy from the initial point. So we are interested only in the total energy, the work done of the particle to move from point B, not from somewhere to point A, but we are interested from point A to point B. That's why we use 7.5 joule minus 1.2 joule is equal to 6.3 joule. Okay, let's proceed. So the next one is regarding the mechanical energy, is defined as the sum of kinetic energy and potential energy. Consider the book Earth system shown here. The book Earth system. So if you have a certain book, when it falls down or from certain height or from the building, so it's considered as the book Earth system shown. Actually, the figure is not included here, so you can assume like that. So as the book falls from YB to YA, the work done by the gravitational force is, the work done by the gravitational force will be minus mg. The book is not going upward. The book is not going upward. The book is going downward. That's why we use from YA to YEB, from YA to YB. YB is the initial position of the book, the initial position of the book. YA is the final position of the book. So YB is, this height is greater than this height. This height is greater than this height. So when you multiply by minus sign, it becomes mgyb minus, which is the final h value, and this is the final one, and this is the initial h value, mgyb minus mgya. This is work done by the gravitational force. Work done by the gravitational force. So the gravitational force at maximum height is larger than the gravitational force at the lower part. Okay, so as the book folds from YB to YA, as the book folds from YB to YA, we have this one, MGYB minus MGYA is equal to this value. Take minus outside, and this become minus, this become plus. When you use minus outside, the YA become plus, this become plus, but the YB, the coefficient of image YB is equal become minus because we have minus outside. So from this, it's possible to write that this is the final potential energy at point A, because it started at point B, then goes to at point A. So this is the final potential energy. The initial potential energy is at point B. Therefore, the change in potential energy is minus value will be equal to the change in kinetic energy of the book is equal to minus of the change in potential energy. This is how we relate the two together, the potential energy and the kinetic energy. Now, when you take this to the left side, the kinetic energy plus this potential is equal to 0 value is a change. Remember, not the sum of kinetic and potential energy. Remember, the change in kinetic energy, plus the change in potential energy, we consider only the change. One may increase, the other may decrease, so is equal to 0. The change in kinetic energy means K final minus K initial, plus the change in potential energy means U final minus U initial. Then it's equal to 0. So K final now takes this minus sign to the right side, it becomes K initial. This is minus, when it goes with the right side it becomes plus. This is minus, when it goes to the right side it becomes plus. So K final plus K U sub final is equal to K sub initial plus U sub initial. So this is the conservation of mechanical energy. Mechanical energy at the point A is equal to mechanical energy at point B. So that's why we say that the sum of the kinetic and potential energy at any point is equal to the initial point or the final point. So all are the same there. That's why we say this is the conservation of mechanical energy. Okay, so the mechanical energy of an insulated system, friction-free system, is conserved. Friction-free system is conserved. Therefore, we have to take the kinetic energy like half mv final square plus something on the surface which is friction-free. Then we have the kinetic and potential energy. Maybe the it goes from certain altitude to downward or down to the inclined plane. So half mv final square plus mgy final is equal to half mv initial square plus mgy initial. So these two values are the same. When you release a certain ball or block down to the incline, when the inclined plane is frictionless, so friction-free. So in that case, we can have this type of formula in order to get the unknown values. Okay, so now we have an example. So in this example, a 3 kilogram crate slides down. This is 3 kilogram slides down a ramp. This is the ramp, slides down from the initial velocity 0. And the length of the ramp is 1 meter. It is 1 meter, and this is V final. We need to get the final velocity. The ramp is 1 meter in length and inclined at an angle of 30 degrees, as shown in the figure below. The crate starts from rest. It starts from rest at the top and experiences a constant frictional force of magnitude 5 Newton. The frictional force of this one is 5 Newton and continues to move a short distance on the horizontal floor after it leaves the ramp. After it leaves the ramp, it continues to move a short distance. We don't care about that, but we need to care about this distance, the initial, the final, then this height. So use the method to determine the speed of the crate at the bottom of the ramp. So we have to get this speed. So in order to get this speed, we have the potential energy here, and we have a kinetic energy, but there is also energy loss due to this friction. Okay, let's use paper for the inclined plane. Okay, so we have this mass, which is 3 kilogram. V initial, as told you before, is 0. Ramp of the distance is 1 meter, and we need to get the V final. This is actually 30 degree, and from the center of mass to here is 5 meter. First we have at the initial point, which is point A. This is point A. We have only potential energy. Therefore, the potential energy at point A, which is equal to mass times gravity times h. Okay, so this potential energy change into 1, that is energy lost due to friction, and the second one is the kinetic energy at point B. Let's say this point is at point B, so the sum of these two will be equal to the potential energy. Therefore, the general formula will be equal to mass times gravity times h, which is the potential energy here, which is changed into 1 due to the friction. Kinetic energy half mv final square here. So from here to here there is also energy change due to friction. So the frictional force is already given, which is 5 Newton, multiplied by the distance of this ramp, which is 1 meter. So when this one goes to here, the energy loss from this point A to point B due to friction is calculated using this formula. Okay, so having this in mind, now let's substitute the values, multiply both sides by 2. It becomes 2 mgh, which is equal to mv final square, plus 2 times this one is 5 times 2, which is equal to, this become 10. Okay, our interest is just to get the v final. So 2 mgh minus 10, which is equal to mv final square. Take 10 from the left side, which is Newton meter, the unit, from the right side, sorry, to the left side, and we'll get this value. Okay, divide both sides by mass, mass cancel by this one, then we'll get 2 gh minus 10 Newton meter over mass, which is equal to the final square. Okay, we know the mass, which is equal to 3 kg, therefore 2 multiplied by 9.8 meter per second square, multiplied by height, which is already given, the height value 0.5 meter, minus 10 Newton meter divided by the mass, which is 3 kg, which is equal to the final square. So when you multiply this together, we get the final, which is 9.8. 0.5 times 2 is 1, so this becomes 9.8 meter square second square, minus 10 over 3, which is approximately 3.3. Again, this is kg, and this one is kg meter per second square. So kg cancel by kg, meter times meter, this is in Newton, which is kilogram meter per meter square. Second square, we final square. Now subtract this one, it becomes 6.5 meter square second square, and v final square. So v final is equal to the square root of 6.5 meter square second square, and v final will be equal to 2.54 meter per second. Okay, the other one is power. Power is defined as the time rate of energy transfer. Power is defined as the time rate of energy transfer. If an external force is applied to an object, which we assume acts as a particle, and if the work done by this force is the time interval change in t, is represented by this one. So the average power during the interval can be written as power is equal to this W, the work done, divided by the interval time, which is change in t. So this is how we get the power. So the instantaneous power, the instantaneous use general formula. You remember from kinematics, where limit change t approach to zero. This is the work done, change the time interval. So that when you change t final minus approach to zero, we'll get work w over t value is will be used for finding of the instantaneous value. Okay, so here in this case, remember that work is equal to force multiplied by change in R, or the dot product of the two, the displacement and the force. So now replace this work by that value, then force dot with change in R divided by change in T. We'll get change in R over change in T is R over T. That is the displacement over time is the velocity. So the power can also be found by using the force as well as the velocity, the dot product of force and velocity. If force is given in a vector form, if the velocity is given in a vector form, and if you are asked to find the power can be found the dot product of the two. Maybe this one is 2I in the J and 3 in the K. So if this one is 5 in the J and 2 in the K, then multiply 5 by 2, 10 plus the other value, so you'll get the power, which is scalar quantity. Okay, in general, power is defined for any type of energy transfer. Therefore, the most general expression of power is equal to energy over T. This is the most general expression we'll see when we see the counting of the electric transfer. So the SI unit of power is joule per second. This is the SI unit of power, also called watt. The watt, which is the SI unit of power. After the name James Watt, it's the name of a person. So 1 watt is 1 joule per second. So this one can be expressed as the joule, which is kilogram meter per second square, which is the force with the distance. There is displacement, there is a meter. So kilogram meter per second square times meter over second. Second square is by second, it becomes second the power of 3. But this one, kilogram, we have meter per second square and another meter. So meter times meter square. So this is a unit for expression of the watt. So in any multiple choice question, you can select this can be equivalent to kg m square over s cubed. So a unit energy or work can now be defined in terms of unit of power. 1 kilowatt is the energy transfer in 1 hour. 1 kilowatt is the energy transfer in hour at constant rate. So 1 kilowatt is 1000 joule per second. The amount of energy represented by 1 kilowatt hour is equal to 10 raised to the power of 3. So watt. This is K means 1000, so that's why it's written 10 to the power of 3 watt times 3600 second. That is the expression for 1 hour, which is 60 times 60, so it becomes 3600 second, or in general it can be written as 3.6 and 10 raised to 6 joule. So this 1 kilowatt hour, let's go back to this formula. This is the power measured in a watt, so multiply with by time, it becomes watt hour. So if you use K, kilowatt hour is equal to the energy. So power is energy over time. So the energy consumption, energy multiplied both sides by T, power multiplied by T represents the energy consumption. So in most cases, kilowatt hour is representative of the energy transfer in 1 hour. Okay, so there is an example. Let's do this example. An older model car accelerates from rest to speed v. Starts from rest means the initial is 0, the final is v. In what second? In 10 seconds. But a newer model, powerful car accelerates from rest again from 0, and the final velocity is to v. The same time period. So what is the ratio of the power of newer car to the older car? We need to find the ratio of newer to the older car. Let's use paper. Power average is work done over the time interval change in t. So for the old car, work of the old car, which we have to use changing kinetic energy, which is half mv final square. We know that half mv final is given v square. This is for the old car. So for the new car, for the new model, we have changing here again, which is half m. The final is 2v square, so 2v square, which is equal to, this is 4 divided by 2, which is 2, therefore it becomes 2 mv square. 2 mv square. Now we have to take the power of the old car, which is equal to kinetic energy, the work done, which is half mv square divided by change in t, and power for the new, which is equal to this 2 mv square over change in t. So power of the new divided by power of the old, which is equal to power of the new is 2 mv square over change in t divided by power of the which is half mv square over change in t. Change in t cancelled by change in t. Mv square cancelled by mv square. 2 times 2, which is 2 times 2 over 1, which is 4. So the ratio will be 4. Okay, the other one that we need to see is momentum is defined as the quality of a moving object to exert a force on anything that tries to stop it. Therefore, this power is equal to the momentum, this is the momentum, which is a vector quantity, not a scalar quantity, which is equal to the mass multiplied by the velocity. So momentum is a vector quantity in the direction of the velocity, they have the same direction with SI unit is kilogram meter per second. For this we have kilogram, this is meter per second. Using Newton's second law of motion, we can relate the linear momentum of particle to the resultant force acting on the particle. So force is equal to m change in v over change in t. The force is equal to m change in v over change in t. Okay, change in v over change in t, we know that it is an acceleration. So right now, instead of writing the acceleration, we have to use change in velocity over change in time. So it's also possible to write change m change in v, where m change in v is the momentum, so change in p over change in t. Therefore, the time rate of change of linear momentum of a particle is equal to the net force acting on the particle. So change in p is equal to f change in t. So the momentum I, which is equal to p final minus p initial, which is equal to f change in t. So multiply this one by change in t, this one by change in t, f change in t is p, where change in momentum is momentum final, momentum initial, which is equal to the impulse. This is again the vector quantity. Okay, so the impulse of the net force F acting on the particle is equal to the change in momentum of the particle. Conservation of linear momentum recalled from the third law, Newton's third law, when two objects, mass 1 and mass 2, interact, meaning that they apply force one with each other, one on the other on the first one. So for example, the object 2 applies to object 1, which is equal to magnitude of an opposite direction with object 1 applying force on object 2. So we can represent F sub 2 is the force on mass 1 from mass 2 or by mass 2, the force on mass 2 from mass 1. So we agree on this. Then the symbol Newton's third law says that F21 is equal to F2. The magnitudes are equal, but in case of the vector, this is minus sign, opposite in direction. That's why it's minus sign. But if you go to magnitude, we will not use minus sign. So F21 is equal to F12. Okay, we start from F21, which is equal to minus of F12, or it's possible to write F12 is equal to minus of F21. It's possible to write in both ways. Okay, it depends upon where the ball is present, considering the x-axis, whether minus x-axis or positive x-axis. Okay, from this we can understand that f12 plus f21 is equal to 0. f12 f21. So the force applied by on mass 2 by mass 1, force applied by on mass 1 by mass 2. So the sum of the two is equal to 0. Now we know that force is equal to mass times acceleration. Therefore f21, we start from this f12, which is mass 1. For f12 you have to use mass 1. So change in velocity v of 1 over change in t 1 plus mass 2 change in v of 2 over change in t1 into 2, which is equal to 0. We know that the change in time is for the two, which is the same, so we multiplied by this number, which is equal to 0 value. Therefore we have finally m1 change in v1 plus m2 change in v2, which is equal to 0. So change in v1 means v final 1 minus v initial 1. Change in v2 means v2 final minus v2 initial. Therefore let's rewrite this one again. m1 change in v1 means v1 final minus v1 initial plus this one mass 2 multiplied by change in v2 means v2 final minus v2 initial, which is equal to 0. Now multiply by mass this one, it becomes mass 1 change v1, not change v1 final minus mass 1 multiplied by this 2, mass 1 v1 initial plus this one multiplied by this 2, mass 2 v2 final, put arrow because it's a velocity, minus mass 2 multiplied by this 2, mass 2 v2 initial, which is equal to 0. Here this one is plus, this one is plus, this is minus, this is minus. Now takes this to the right side, this one to the right side, the minus sign to the right side, and leave this one as it is. Then we'll get m1 v1 final plus m2 v2 final is equal to m1 v1 initial plus m2 v2 initial. So this one is the first one, which is the final momentum. This is the initial momentum. So it shows that there is a conservation of linear momentum. So law of conservation of linear momentum is satisfied. So we can say that P total is always equal to P1 plus P2. P1 plus P2, which is always equal to constant. This is always constant. So that's why we get this result in case of linear momentum. Okay, so having this in mind, we can do this question. So it says that a 60 kilogram archer stands at rest on a frictionless ice and fires 0.5 kg arrow horizontally at 50 meters per second. With what velocity does the archer move across ice after firing the arrow? Okay, now let's use paper again. Okay, let's consider this is the archer. This is the archer, the person standing on a frictionless ice. So the mass of the person is 60 kg, and the mass of the arrow is 0.5 kg. So the arrow released with the speed of 50 meters per second. So we'll apply momentum, the initial momentum and the final momentum. M1 V1 initial plus M2 V2 initial is equal to M1 V1 final plus M2 V2 final. Both starts from rest, that's why this becomes 0 and this becomes 0. So 0 is equal to M1 V1 final plus M2 V2 final. So mass, let's say this one, the person, the mass of the person, which is 60 kilogram. Let's say M1, so 60 kilogram for M1 times V1 final is unknown, and mass of the arrow, which is 0.5 kg, multiplied by V2 final. V2 final is known, which is 50 meter per second. Multiply this one, it becomes 25 kg meter per second, and takes this to the left side, it becomes minus 25 kg meter per second. Divide by 60 by 60, it becomes 0.42 meter per second, and minus. The minus sign indicates the direction. This minus sign indicates the direction. So when the arrow goes in this direction, the person will go to the left side with a speed of 0.42 meter per second in the negative x-axis. Considering this one positive x-axis, this is the negative x-axis, so the person goes in the negative